In this video, I want to take a look at the notion of orthogonal complements and some theorems related to that. Here's the definition. If W is a subspace of Rn, then the set of all vectors in Rn that are orthogonal to every vector in W is called the orthogonal complement of W and is denoted as this. We sometimes call this W perp. Right? There's a perpendicular sign there. So you've got some subspace W, and you're looking for everything in Rn that's perpendicular to everything in W. Now I say perpendicular because I'm okay with the notion of perpendicular in Rn. The book is very careful and it always says orthogonal, meaning dot product equals 0, right? So let's take a quick look at a couple of examples here. So in R2, subspaces are either just the origin or the whole, or a line through the origin or the whole space. Right? So if my subspace W, say, is this black line through the origin, then W perp is all the stuff in R2 that's perpendicular to everything that's in here. Well, that would be this blue line, right? Notice if you took any vector that's on that blue line and you dotted it with any vector that's on that black line, then they would be perpendicular to each other. The dot product would be 0. Right? If you took something that's not on the blue line and you tried dotting it with something on the black line, well, I mean, you can clearly see you're not perpendicular, so the dot product will not be 0. And that would not be in W perp. So if W is the black line, then W perp is the blue line. In R3, let's see, in R3, it might look like this. Suppose W, so in R3, first of all, subspaces could be just the origin, or lines through the origin, or planes through the origin, or the whole space. So let's say that W is the black line. Well, then I claim that W perp is this blue plane. Let's see, can I? Right. So that any vector that's on that blue plane, I claim is perpendicular to every vector that's on this black line. And I can see they're perpendicular if I put that plane in projecting position here. And you can see that that's a right angle there, at least I hope it is. It's supposed to be. Unless I have something typed in wrong. Orthogonal complements. Now, theorem here about orthogonal complements. I must admit I have one more thing in this theorem than the book does, but here we go. First of all, W perp is a subspace. I will not prove that here. I will leave that to you, the student, to prove. Or would maybe ask you to prove it at some point. Quiz, test, I don't know. So you might want to figure out how to prove that it's a subspace. I mean, I'll mention we do know how to prove things are subspace, right? You have to show that they're closed under addition and scalar multiplication. Not too hard to show. The two examples that I showed, of course, were a line in the plane whose orthogonal complement is also a line through the origin, and a line in space whose orthogonal complement was a plane through the origin. Right? So yeah, the W perp is a subspace. The intersection of a subspace and its orthogonal complement is just the 0 vector. Right? In these two examples, right, those lines only crossed at the origin. In R3, the only point common to the black line and the blue plane were the origin. Right? That the intersection is just the origin. Number 3 here is that the orthogonal complement of the orthogonal complement of W is W. Right? That W perp perp is back to W. And again, you can see that in these images here, that if this blue plane is everything that's perpendicular to everything in the black line, well, then the black line is the stuff that's all perpendicular to everything in the blue plane. And lastly, and this fourth part is not in the textbook, but I want to include it here, that the dimension of the subspace W plus the dimension of its orthogonal complement is always equal to n, where n is the Rn that you're in. You're in an n-dimensional real space, then the sum of the dimensions of the subspace and its orthogonal complement is n. Okay. To prove this last one, I'm going to need a few other things, but in particular, I'm going to need a theorem here that's in the book, and it says if A is an m by n matrix, then the null space of A and the row space of A are orthogonal complements. Likewise, the null space of A transpose and the column space of A are orthogonal complements. Now we've seen. Well, here's my proof. I'm relying on the fact that we've seen in the past that the solutions to the homogeneous system AX equals 0 are all orthogonal to the rows of the matrix A. We've proven that before. I mean, the whole idea is that AX equals 0. When you take this, how do you do this matrix multiplication? Well, you dot the vector x with the first row of A, and it has to equal 0. And then you dot the vector x with the second row of A, and it has to equal 0 all the way down the line. So that x is definitely perpendicular to all of the rows. The question is it perpendicular to all of the whole row space? Because the row space includes all the linear combinations of the rows. So could there be a linear combination of those rows that's not orthogonal to x? Well, the thing is, we know that x is orthogonal to each one of the rows for I equals 1 to n. Actually, this should be I equals 1 to m because there's m rows in this matrix. Now, let V be any vector in the row space of A. So what do I know about vectors in the row space? I know that they are linear combinations of the rows. So for some values, k1 up to km, I can multiply each of those by the rows of matrix A and end up with the vector V. Now, I don't know that the rows are independent, so I don't know that this is unique in any way, but I know that it can be done. If you're in the row space, you're a linear combination of the rows. So, what I want to see is this vector perpendicular or orthogonal to this x? And all I know about x is that it's in the null space. So anything in the null space times anything in the row space, dotted with anything in the row space, is it equal to 0? Well, let's see. The thing is, if I dot this vector v with x, then I know v can be rewritten this way, as we just said, and so dotted with x, and then I know that the dot product has a distributive property over vector addition, so I can dot it with each of those vectors. And then I also know, although I didn't write it, is that I can do the dot product before. This is another one of the properties that you can do the dot product before multiplying by that scalar, or you can multiply by the scalar first. But let's do the dot products first, because I know from up here that these dot products, row 1 dotted with x and row 2 dotted with x, all the way up to row row m dotted with x, I know that those are all equal to 0. So this is 0 times k1 plus 0 times k2 plus 0 times k all the way up to 0 times km, right? And that would be a grand total of 0. So yes, everything in the null space is orthogonal to everything in the row space, and they are orthogonal complements. Now, to do the null space of A transpose, well, the null space of A transpose would, by part 1, would be the orthogonal complement of the row space of A transpose. But the row space of A transpose is the same as the column space of A. So the row space of A transpose and the column space of A are orthogonal complements. Now, going back to number 4 up here, I want to show that the dimension of any subspace plus the dimension of its orthogonal complement is n. Right? What I know already, at least for some subspaces, because I know that the dimension of the null space, which we call the nullity, plus the dimension of the row space, which we call the rank, has to be n. We showed that in the last video. Okay. So, but the row space and the null space aren't just any arbitrary subspaces of Rn. They're very specific ones. They're ones that come from a matrix, and you're saying, look at the span of the rows, look at the solution set of Ax equals 0, right? Those are very specific types of subspaces. However, I'm claiming this is true of anything. That is, yeah, row space and null space are orthogonal complements and their dimensions add up to n. But you take any subspace and you add the dimension, take the dimension of any subspace and you add the dimension of its orthogonal complement. You always get n. And the way that I can do this is to show this. That is, every subspace of Rn, no matter what subspace you have, it is the row space of some matrix. And my proof is as follows. Take a basis for that subspace. Now, in one case, it doesn't have a basis. If that subspace W is actually just the zero vector, well, then that's the row space of a zero matrix. Right? Take a 1 by n matrix. That's all zeros. Right? The row space of that is the zero. Now, if it's not just the zero, then it has some non-zero entry in it. So it also has to have a basis in it because it has some linearly independent vectors there. So if you've got a subspace that has at least one non-zero thing in it, take a basis for that subspace. Now make a matrix whose rows are the basis vectors written as rows. Right? So basis vector 1 is the first row, basis vector 2 is the second row, and so on. Notice that that matrix will be some number of rows, however many basis elements you have, by n. And it's by n because each of those basis elements is an element of Rn as well, right? Because the subspace is in Rn. So it has n entries in that list of numbers. So your matrix would be something by n. And then we ask, what is the row space of that matrix? Well, it's the span of the vectors that are the row vectors, right? And the row vectors are the basis for the subspace you wanted. So you have that subspace now as a row space of a matrix. And that same matrix has a null space. And the null space is the orthogonal complement to its row space. But the row space is the subspace that you started with, W. And so we know that this row space and its corresponding null space are orthogonal complements. And we also know that the nullity and the the nullity and the rank of that matrix add up to n. And so we have shown what we wanted, that the dimension of W, which is now recognized as a row space of some matrix, plus the dimension of W perp, which is the null space of that same matrix, have to add up to n. The dimensions add up to n. Okay. Now there's one more theorem in this section that we need to take a look at, but I think it deserves its own video, and we will do that next.